So this is the second part of the video on the pumping theorem, and in it we'll actually define the pumping theorem itself. So you should be comfortable with the regular languages and deterministic finite state machines, and you should be reasonably comfortable with what was discussed in the first video, which is that long strings go through cycles in deterministic finite state machines, and what we mean when we say we are pumping a string in or out. So just to recap, if we have a language which has a minimum DFSM, this DFSM will have a certain number of states. Any string accepted by the machine that has more symbols than the machine has states, or at least as many symbols as the machine has states, then some part of that string has to traverse a cycle of states in the machine. If that doesn't make sense, go back and watch the previous video, part 1. We also showed in that video that the finite languages are regular. If we have an infinite language, then there must be no upper bound on the length of the strings in that language. So there is definitely within that language some string which has as many symbols as the machine has states, for which the above will hold. So there will be a string in the language which can only be accepted by traversing a loop in the machine. When we do have such a machine that goes through a cycle, when we do have such a string that goes through a cycle, then we showed in the last video that we can pump it in as many times by reinserting it over and over in the middle, or we can pump it out by removing that bit that is accepted by the cycle. The bit that traverses the cycle. Okay, let's say that we have a regular language and a machine which accepts it, which looks something like this, and that this regular language is infinite. So what that means, as we talked about before, is that there must be some loop somewhere in the machine that accepts this language, because otherwise we couldn't have unbounded length strings accepted by the machine. And let's say that we have a particular string from the language, W, and this string from the language is longer in length than the number of states that the machine has. So this means that we know that this string must go through at least one loop in the machine. So, saying that we have that, we can then look at the hypothetical machine that accepts this string W and know that there is one loop, the first loop, that the string goes through somewhere in the machine. So, let's say that this string is accepted and follows this path through the loop and then goes and does something else. So what we can say is that the first part of the string we can denote as X. Then we have a part of the string that is the first bit to go through a loop and the bit that goes through that loop just once. And we are going to call that Y. So are you following? We've gone up to the first loop, and at everything up to the start of that first loop we're calling X. Then our first traversal through that loop we are calling Y. Then the rest of the string W, which may include going back through that loop another bunch of times, going out through some other states, through any number of other loops, and finally hitting the accepting state, we are going to call that part Z. So we can see that if we have a string that is long enough to force a traversal through the loop, then that string can be written as 3 parts, X, Y, and Z, where X is everything leading up to the first loop traversal, and that may be empty. If this start state is where the loop starts, if this is the same as this, then X would be an empty string. Y is the part of the string that goes through the first loop once. Now that can't be empty because this loop is in a deterministic finite state machine and therefore covers at least one transition, which means that at least one symbol from the alphabet has to be consumed. So Y can't be empty. Then we have the rest of the string, which may include going back through that loop a bunch of times or going off to other start parts of the machine or even coming back. But everything that goes from the end of the first traversal of the loop up to the accepting state, we call Z. So just to summarize all of that a little bit more formally, we are saying that if we have a long string, W, then we can break it up into 3 bits, a first, middle, and a last bit, which we call X, Y, and Z, where X is the start part of the string that is accepted by, that is processed by the part of the machine leading up to the start of the first loop. So it can't go through a loop. But we said that the first loop may start with the start state, so we know that X can be empty. Now Y is the part in the middle of the string, middle so to speak, which goes through that first loop once. And Z is the part of the string processed from then onwards and may go through any other remaining parts of the FSM and any number of other loops and eventually hits the accepting state with nothing left in the string W. So just to reiterate, because we're discussing deterministic finite state machines and we're saying that Y is the part that goes through a loop, which we know it has to because we said that the string is long, then we know that Y cannot be empty. But X or Z may be empty. So Z may be empty as well. If the machine just consists of a loop where the start state is the accepting state and this particular string just goes through that loop, then both X and Z would be empty. So we said formally that what we mean by a long string is a string where the number of symbols in the string is greater than or equal to the number of states in the minimum DFSM that accepts the string. Correction, accepts the language. So we iterated that we can break the string up into 3 parts, X, Y, Z, where the middle part Y is a single traversal through the loop, so it cannot be empty, but the start and end parts are the part that leads up to the start of the loop, which may be empty, and the part that consists of the remainder of the traversal of the machine, which may also be empty. But we have one extra limit, which is on this start part, X, Y. So what we said was that it was the part where we came in from the start state, and then we traversed some states, hit a particular state which indicated the start of that loop, and then we traversed that loop once. So because we've visited only the one state more than once, and every other state we've only visited once, we know that there cannot be more symbols in X, Y than there are states in the machine. So we have this limit on X and Y, which is that the length of XY is less than or equal to the number of states in the minimum DFSM, which we're going to denote later by lowercase k. So, we said in the first video that if we have a section of a string that goes through a cycle in the DFSM, then we can pump that in or out. Now our assumptions were that Y was the section of the string that went through the cycle in the machine, which means we can pump out Y or pump in Y as many times as we want. What that means formally is that if W is accepted by the machine, and that was our original assumption, and W is a long string, if we break it up into the sections X, Y, and Z such that Y is the section that goes through the loop, then this set of strings must be in the language as well. They must be accepted by the finite state machine. And they are the strings that are made up by repeatedly inserting Y as many times as we want between Y and Z, or by removing Y entirely. So what that means is that the strings X, Z, X, y, y, z, or x with 10 y's one after the other, are all accepted by the machine. Now remember, x, y, and z are not symbols, they are sections of the string, so they are strings in themselves. So let's say concretely that we have a string w accepted by a finite state machine, and this is a long string according to our definition, and we will call that string 1ab0, 0. And let's say that the middle three characters are the part that traverse the loop. So x is the 1, z is the 0 at the very end, and y is the middle string ab0. That means that the string 1, 0 must be accepted by the DFSM. The string 1ab0, ab0, and then a 0 must be accepted by the finite state machine. And the string where we insert ab0 over and over again between the last occurrence of ab0 and the end 0 must also be accepted by the machine. Since they are accepted by the machine, they are trivially members of the language which the machine accepts, obviously. So finally, we've now arrived at what the pumping theorem is, which in layman's terms says that we have a language, if we have a language L, which is regular, then we can take any long string in that language and break it up into three parts, x, y, z, one after the other, where the first two parts contain less than k symbols, and the middle substring, which is y, is a non-empty string, and all of the strings made up by pumping that middle substring either out of the string or into the string a number of times are all also members of L. So this long formula is the pumping theorem formally. So it is a statement that holds true for any regular language, and it says that there exists an integer k greater than or equal to 1 such that, and then all of this holds, for all of the strings in the language that are long strings, so where the length of the string is greater than or equal to this mythical k, then this long bit is also true. So, for any regular language, there exists a k such that for any string longer than k, this bit that I'm about to explain to you in red is true. And that is that there exists an x, y, and z, which are strings, such that we can represent w as x, y, and z. And this is exactly the same as we said before, where the number of symbols in x and y put together is less than or equal to this k value, which specifies the minimum length of a long string for the language, and y, the middle bit, is not empty, and all of the strings that we can make by either removing y, that is setting this q to 0, or repeatedly inserting y between y and z, are also in L. So this looks long, but it's actually a very simple statement that is true for all regular languages. So that means if we ever find a language that this statement is not true for it, then that language is not regular. So what we will show in the lectures later is that we can use this theorem, which says that this property holds for all regular languages, to prove that languages are not regular. So you don't use this to show that a language is regular, because you do that by either building a finite state machine or making a regex or making a regular grammar for it, or showing it through the closure properties. But you use the pumping theorem to show a language is not regular, and that's what we'll do in class. So, after this set of long, dry, complicated videos, you should have an understanding of what the pumping theorem says for regular languages. If you want more information, you can look at section 8.4 in the textbook, but honestly, I'd wait until after you've gone through the lectures.